there, folks. Back here with another video in our study of the derivative, where we're taking a look this time at what we might think of as another fundamental or basic rule of derivatives, right? However, it is just the case for one type of function, or even really we should say just one function, that being the natural exponential function, folks. Let me bring this into view here. Let me bring over my notes. All right. We're going to talk about the derivative of the natural exponential function, folks, where if we take note or recall, the natural exponential function is the function f of x equals e to the x. Right? It is the function described by the exponential function, right? A function whose base is a real number. In this case, its base is the value e known as the natural number, or what's sometimes referred to as Euler's number. And that base is raised to the independent variable of the function, x. Right? This forms what we call an exponential function, and because it has the base of e, it's more specifically known as the natural exponential function. And it is the case of it's a unique case of a function, an exponential function, a unique case with respect to its derivative. All right? To begin with, e is an interesting number. It is called the natural number, and I do give it here by definition. Right? There's a few ways here that we see its definition, right, presented. Right? E is the irrational value, where we think about e being about 2.718 or about 2.72, are common approximations that we give for e in its irrational behavior. Right? But in terms of its exact value, the way that we define it exactly is using this limit statement, or a variation of this limit statement being this limit statement seen here. They're both really saying the same or describing a very similar behavior, right? Where the difference lies between how we use this reciprocal of n and this power of n, right? And the behavior of n in the limit. Otherwise, they are saying basically the same statement, and that is that they are giving us the value of e. They are approximately, if we were to use a table method to approximate this limit, they are approximately 2.718 in value, right? Or if we go on to study Taylor series or infinite series, a topic that we're going to see in Calc 2, right? What we will see is e defined as what we would call this infinite summation. Here we can see e is defined as this infinite summation involving an argument of 1 over n factorial, right? Where if we think about the pattern here, starting at n equal to 0 and continuing up through infinity, right? Would form the pattern 1 over 0, 1 over 1 careful there, 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, plus 1 over 3 factorial, on down the line. All being added up sequentially. Right? Where, if you remember, what is a factorial? When we talk about a factorial value, like 3 factorial, it is the number of ways to arrange 3 items, is how that is defined. Right? If we think about having 3 items, maybe the letters A, B, and C, if we think about the different ways we can go about rearranging those 3 letters, well, there are 3 factorial ways. And the way that we evaluate a factorial is we take that value, 3 in this case, and we multiply it by the integer value, or 1 less than it, in pattern all the way down until we take away 1, then we multiply by taking away 2, and then we multiply by taking away 3, all the way until the final numbers in the pattern are times 2 and times 1, which is not far for 3. Really, 3 factorial is just 3 times 2 times 1. 2 factorial is 2 times 1, and 1 factorial is just 1. As for 0 factorial, it is just the value of 1 itself. Remember, a factorial is the number of ways to arrange that number of items. So how many ways can you arrange nothing? Well, there is one way to form that arrangement. So that would technically be 1 over 1. 0 factorial equaling 1. The value 4 factorial would be the number of ways to arrange 4 items, and there would be 24 ways, because it would be 4 times 3 times 2 times 1. Where we know 3 times 2 times 1 is 6, times another 4 would produce the 24. Right? If we take these ratios of 1 over our successive factorial values and add them up, right, they will add up to the value of e. And we will explore this infinite summation when we get up into Calculus 2 and we talk about infinite series. Right? Now in calculus, we do also have a definition for e. Let me bring this up. And the way we think about it in calculus, e is about the value, 2.718, that satisfies the following limit. The limit as n heads to 0 for e raised to the n power minus 1, all divided by n. Where that limit, we say, is equal to the value of 1. Right? E is the value that makes this limit true, is what we say in calculus. And we will use this result. What we'll see later on is in the proof of what's going to be our derivative result for the exponential function, the natural exponential function. All right. Now, we can show this limit is true using a little bit of squeeze theorem. So you'll notice that's the first thing I do in the notes here. It's because we rely on this limit, I like to show that this limit is true. All right. And it can be proven true with a little bit of squeeze theorem. All right. By noting for n greater than 0, our argument of the limit is stuck between the reciprocal of e to the n and e to the n itself. And when n is less than 0, we have that same behavior, except that the sign, right, the direction of the inequality changes direction, right, for the case when n is less than 0. Now, the easiest way to say that these inequalities are true quickly without spending the entire lesson on just defining and showing these inequalities as true is to look at it graphically. Right? If we look at the graph of these relationships, right? Here we have the graph of the three functions in these relationships, e to the n minus 1 divided by n, and 1 over e to the n. And we can see on the right, where n is greater than 0, this being the axis for n, e to the n minus 1 divided by n is smaller than e to the n and greater than 1 over e to the n. This relationship is true graphically for n greater than 0, we can see. For n less than 0, on the left side of the graph, right, over here on the left side, we can see that's true, right, in the reverse order of that inequality. 1 over e to the n is the largest. It's greater than e to the n. No, hold on. That power is in the wrong spot. Let me fix that. I'm glad I went through this. Spot that error. Minus 1 divided by n, which is greater than or equal to the value of e to the n. E to the n of this is the smallest dependent value when n is less than 0. Right? We see that in this relationship. These two inequalities are true when we consider these behaviors for the value of n. Right? Now, if we take note of what the limits are for the two ends of that inequality in both cases, as n heads to 0, what we would notice is 1 over e to the n and e to the n would both behave the same way. And we can see the result here in the graph. They both approach the value of 1. Right? To begin with, we know if we consider the limits of all three parts of that inequality, the outside and the inside, the two outer limits equal the value of 1. So that means the limit that we're interested in must be also stuck between those values of 1 and must be equal to 1 itself from the squeeze theorem. Let's bring this up. Right? Implying that this limit here must also equal the value of 1 from squeeze theorem. And similarly, we can show this same result for the inequality for the case when n is less than 0. I just show the case for greater than here, but it would be the same for less than 0, more or less just changing the sign of this inequality here. All right. What's a little bit more of an interest to us, though, is the derivative of e to the x. It has an interesting result. If we set up the derivative of f of x equal to e to the x by its definition, right, and we say that we're looking at f prime being the limit as little h heads to 0 for f of x plus h minus f of x all divided by h, the defined value of the derivative, when we substitute in x plus h into our function f, we develop the value of e to the x plus h. And we're going to take away from that f, which is e to the x, and divide that all by h. Where e to the x plus h can be rewritten. Rewritten so that it involves a factor of e to the x. And we see that done here in this next step. E to the x plus h from the rule of powers from algebra says that if you have the product of two powers with the same base, like I have here in this highlighted statement, they can be written as a single power with the same base if we add together the exponents, which we're doing with x plus h. So e to the x plus h can then be rewritten as e to the x times e to the h using that power rule. Now that e to the x in both of these terms is a common factor, and we can factor it out of each of those terms. Right? So I'll bring it all the way out in front of the group, and what we'll leave behind in the group is e to the h minus 1 then divided by h, which should look familiar from above in the limit argument that we define using e. Now, this limit, when it goes to evaluate this group, this e to the x can be thought of as a constant multiple. It doesn't involve h. So it is constant with respect to h changing and heading to 0. So we can factor that e to the x out as a constant multiple. And we're left with the limit as h heads to 0 for e to the h minus 1 divided by h. Where we know that limit from above is equivalent to the value of 1. So here we have just e to the x times 1 in a sense, which is simply e to the x. And thus we can conclude for the natural exponential function f of x equals e to the x, its derivative is f prime of x, which is also equal to the value of e to the x, which is a really interesting result there. The derivative of the natural exponential function is itself, which doesn't happen for any other function type other than the constant function of 0. The derivative of 0, being the derivative of a constant, is also equal to 0. And that's the only other function type whose derivative is equal to the function itself. That's also true for the natural exponential function. And we say that in this theorem. Right? For our natural number e, which we maybe should note is approximately the value 2.718, right? The derivative with respect to x for e to the x is equal to, right, as we have proved above, the value of e to the x. So although the above is a little bit complex in terms of the theory and the value of e, the derivative result for e to the x is pretty fundamental, just being the value of e to the x itself. All right. Now, let's just work it into a quick example to finish up this set of notes. For example, we might be given y equals x cubed times e to the x, where in the product rule, if we set this up, it will be the product, well, from the product rule, it'll be the first factor's derivative times the second, which we state right here is the derivative with respect to x for x cubed times e to the x, plus the first factor times the derivative of the second, e to the x, which we would set up as x cubed times the derivative with respect to e to the x. And we know what these two derivatives are. Derivative of x cubed is 3x squared. Derivative of e to the x with respect to x is also just e to the x. So, if we bring those results in, this statement will simplify into 3x squared e to the x for this first term, simplified, and the second term will become x cubed e to the x because the derivative of e to the x is simply, again, just e to the x. Now, if we do factor that, which is something we're going to want to work on, right, as we get into a little bit of application of derivatives, the factored form is going to be helpful. So, just taking a quick note, factoring produces, well, a common factor of x squared and e to the x. So if we factor those out of our two terms, we'll be left with 3 plus x in the terms. And we'll have that common factor of x squared e to the x. Right? Just a quick little example with that result. But this is just a single result for a function, folks. But an interesting case. But a very interesting case. All right? The case for the derivative of the natural exponential function. We're going to be using this knowledge a little later on when we consider the derivatives for just exponential and logarithmic functions in general. Knowledge of the derivative of e to the x being e to the x is always going to be helpful. We're going to see that. Right? And this will make a little bit more sense, right, as we continue our study and start to learn that derivatives represent instantaneous, or they describe instantaneous rate of change in our function. And what this is saying is that the instantaneous rate of change in our function e to the x is described by e to the x. And e becomes known as that natural number because it does represent, in a sense, the case where the instantaneous rate of change in our function occurring naturally would be occurring at a rate described by e to the x, the natural number. We're going to talk about that here when we start to get into some of the application, right? So I will end that video there. This was pretty much a quick video, just taking a look at the derivative of the natural exponential function with a little bit of definition to begin with to help define out e for us, and then prove our result. We proved it by definition and using a part of that definition for E, and then looked at a quick little example at the end. All right, but other than that, it is a rather fundamental result, folks. Take note. And we will see it work itself into some of our some of the calculus we see from here on out. So take note. But with that said, I will end this video, and I will see you in the next one.